Hi, I'm Justin Essery. This is Pol 280 Research Methods. And today we're going to talk about sampling and probability distributions and just begin to talk about statistical inference using data from samples, which is almost always the data we have. So if you're in the actual class Awake, you can log on to the RStudio server and get ready to get started. If you're watching from somewhere else, you can go to my website, download the R script and the data files that are necessary to follow along the lecture, and do it that way from your home computer. All right, let's get started. All right, so the question we're going to try to answer today is how you can determine something about a population, such as voters in the United States, using only a small sample of that population, such as respondents to a poll or a survey conducted among people in the U.S. As I mentioned at the very beginning of the video, we almost never have a full access to a full population of data. We can't generally survey every single person in the United States, for example. And even in cases where we might have access to the entire universe of data that's available. So for example, even in cases where we have data from all countries over a certain period of time, right? Like in the quality of government data set. Even in that situation where we do have a population, we only have one snapshot of things as they occurred at one point in history. We don't necessarily have the population of all the events that might have occurred if small random things had gone slightly differently. And so even in cases where we have, in some measure, a population, we often still consider that a sample because we consider it a sample out of the possible histories that might have unfolded. If we rewound time and sort of played things back again, things might unfold slightly differently. And if you were to do that over and over, you would get a sort of different outcome every time, slightly different, maybe substantially different, depending on how linked to randomness the outcomes are. So even in cases where we have a population, we often assume that we have a sample from the population. And of course, in a lot of cases, we certainly don't have a population. So when we do surveys, research, for example, we almost never have a survey of every person in the U.S. The census has some of that data for the U.S. If you literally conduct a census where you're measuring every single person, sometimes you have that. Almost always we don't, though. So the data set we're going to use is from the Consumer Expenditure Survey of the Bureau of Labor Statistics in the fourth quarter of 2016. You can see I have a link here that shows where that data comes from. This is a survey of consumers in the United States conducted by the U.S. government. And the question we're going to ask is how much people in the United States make on average. And so I've got this data file here, fmli164.dta. This is a stated data file, but we're going to open it in R. You can access it from this link. But it's already been loaded onto the RStudio server if you are in this class at Wake. So we can just go into RStudio and load it up right now. Okay, I've got my RStudio server open. You can see rstudio.justinessery.com. Here's my R console. And we want to open that data set we just mentioned. So the first thing we need to do is navigate to the Pol 280 directory in the files pane here so we can get access to the data. And also I prepared a little script of all the commands we're going to use today. So if you scroll down in here, you'll see probability-distributions.r. If you click on that, that's a little script file that has the stuff we're going to do today. And it enables us to very quickly access the data and start work. So the first line clears out memory. I've got to clear memory already because I just started this new session in R. I'm going to set the working directory to the Pol 280 directory. I'm going to use the Haven library to load in data, load in, what do you call it, Stata data set, which is this fmli164.dta data set, which has already been uploaded into RStudio. And now we're ready to go. You can see there are 6,301 observations of 809 variables. So this is a survey where they collected a lot of information. We're only going to focus on a small subset of that information, which again is pretty typical when you're doing this kind of research. All right, so this is a class about sampling distributions and probability distributions. And so before we get into any actual analysis, we need to define some terms. So a population, in the language of statistics, is a group that you're studying and a complete collection of the entire group that you're studying. So, for example, this is 2018. If you're trying to predict an election outcome in the United States in 2018, the population of all voters in the particular election unit that you're studying, let's say a congressional district, that is the population. Everyone who is going to vote or who has voted in a particular district or electoral district, like a congressional district, that is the population. And of course, we will collect that information on election day, right? Everyone's going to go to the polls and vote. But if we're conducting a survey in advance of that election, probably we're not going to survey hundreds of thousands or even tens of thousands of voters. Certainly not if we were looking at a presidential election like in 2020. We're certainly not going to ask millions and millions and millions of presidential voters all the time to see where they are. We're going to collect a sample of those people. So you can see sample here. A sample is a selected proportion, a subset of the population that we're studying. So for example, I might try to in some way randomly sample 1,000 or 2,000 voters from an electoral district, like a congressional district, and ask them who they're going to vote for. Or I might ask them if the country's on the right track or the wrong track. Whatever it is that I want to ask them about, I'm not going to ask the entire population. I'm going to ask a sample. And of course, the trick here is I don't necessarily care about that sample. What I really care about is the population. So what I really want to know in an election, for example, is who's going to win. And in order to know that, I need to draw a conclusion about the population, right? About all the voters. I can't get them. I can only get a sample. And so I have to use the information in the sample to draw a conclusion about the population. This is, I think it's fair to say, the heart of what it means to conduct inferential statistics. We are using a small subgroup of people to draw an inference about a larger subgroup of people, or states, or whatever the unit of analysis we're studying. And as I mentioned before, even in cases where, for example, we have all the information about a bunch of states over a certain time, and so we, in some sense, might have a population, we typically treat that data as though it's a sample, as though if we were to rerun history over and over again, we would get slightly different results. And so what we actually see is in some sense a sample of what might have occurred. So a probability distribution is a mathematical function telling you the likelihood that a certain value will appear if you draw an observation from a random of a random variable. And this links to sampling because when we sample, we are more likely to get certain types of people and less likely to get other types of people, depending on how likely those particular types of people are to occur in the population. And what a probability distribution does is it tells us how likely we are to observe a certain kind of person or a certain, whatever characteristic in the sample that we draw. So I'm actually going to skip this for a second and go forward. This is an estimate of the distribution of household income in the United States in 2014. And what you can see here, there's a histogram, right, which we've already studied underneath. On the x-axis is income. Higher incomes are higher, lower incomes are lower. I have to note they didn't put the actual values of income on the x-axis. That's generally a bad idea. You always want to label axes so you know what you're looking at. They have provided a couple of targeted labels, which I guess is helpful. And then there's this red line, which is a fitted probability distribution to the data that is described by the histograms. So what this red line is trying to tell us is essentially how likely we are to observe a person, or in this case a household. Household is the unit of analysis. A household with a particular value of income in 2014. So if you were to draw a random household out of the United States in 2014, you just picked one at random, the most likely house income that household would have is $12,300 $300 per year. That is the modal income, which is the most frequently occurring income. It's got the highest value of the probability density. You can see it's the highest value. It's also the 10th percentile, which means that essentially 10% of incomes are smaller than $12,300 in this data in 2014 in the United States. So the most frequently occurring number is actually not. In other words, it's not like half of households have less income. It's actually sort of a very small number comparatively. Only 10% of people have a smaller income than $12,300. That's because this particular distribution is pretty right skewed, meaning there's a long tail that goes off to the right. So what that means is there's a small number of people who have very, very, very high household income. The 50th percentile income is $53,700 for a household in the United States in 2014, which means that half of households have an income less than $53,700. And you can see this outcome is sort of in middling likelihood to occur based on the probability density. And then the 90th percentile, so 90% of households in the U.S. make less than $157,500. And that's actually a fairly low likelihood to occur. And then finally, the 95th percentile is $206,000. Again, this is for an entire household. So if there are multiple earners, you add them together. So if two people make a little over $200,000 or a little under $100,000, the household income is $200,000. And you can see here, whoops, that's a relatively low likelihood to occur. But then this tail just sort of keeps on going. So there's a small but non-zero probability that households make a lot more. So when we talk about, the 1% or the 5% you may have heard in political rhetoric, this is what we're talking about, right? So 5% of households make more than $206,000 per year, and it's a lot less likely to occur than a household making $12,300, which is the most likely, the most likely thing you would get if you randomly drew a household out of the United States in 2014. So this red line is our estimate of the probability distribution of household incomes in the United States. So, going back here, the probability distribution is that curve which tells you the likelihood that a value will appear if you draw a single observation from a random variable. So when we're sampling, if we were to draw a sample of households out of the United States, we would be most likely to draw households with around a $12,000 household income. But there would be a substantial probability of drawing a household with $53,000, a somewhat less probability of drawing $157,000, and a very, very small probability of drawing with, let's say, $500,000 or $1 million. So that's what a probability distribution is. A sampling distribution is the theoretical probability distribution of a particular statistic across all possible random samples. So what you would call the sort of trick here is a mean is a random variable. So, for example, if I were to take a sample and calculate the mean of that sample, and then I were to take another sample and calculate the mean of that sample, and then I were to take another sample, a different sample, and calculate the mean of that sample, the mean would be different each time because the sample would be different each time. And so we can consider a sample statistic, like the mean, a random variable. And the source of the randomness of the variable is the sampling process, which comes up with slightly different people or units every time. And so if we think about the probability distribution of a sample statistic, like a mean, that's something we would call a sampling distribution. So, for example, this is the probability distribution of incomes in the U.S. We could also think about there being a probability distribution of the mean income in the U.S. That would be the sampling distribution of the mean income in the U.S. And that would be the distribution of the sample of a particular sample statistic, the mean, if we were to repeatedly draw samples from the United States in 2014. We would get a slightly different mean every time. That mean would move around a bit, and we get a distribution of that. It's probably easiest to understand this if we see a little sample of how this works. So let me load up an applet that will give you a sense of what a probability distribution is, what a sampling distribution is, and how those two things are related. Okay, so what we're going to do to demonstrate what a sampling distribution is do a little computerized simulation. And the way this simulation is going to work is we're going to specify a probability distribution for a population. We're going to repeatedly draw samples from that probability distribution from the population, so that's going to create a sample. We're going to create a sample statistic from that sample, in this case a mean, and then we're going to repeat that whole process 10,000 or 100,000 times, and every single time we're going to get a slightly different mean. And what you'll see is that those means from each of the samples form their own probability distribution, which we call a sampling distribution. So the link for this simulation software is here, and I already have it pulled up right. So it's off the RStudio server here, and so you can see right here in the top graph, what we have here is a population distribution. This is for some statistic, goes from 0 to 32. Don't know what that is. Maybe it's age in a particular school or something. And we can redraw that population distribution to be anything we want. So what I've redrawn it as here is a sort of a bimodal distribution with two most frequently occurring numbers, two modes. This could be something like a height distribution, maybe, for men and women. Women tend to have a lower average height than men and tend to have a lower, most frequently occurring height than men. So if you put both of those two populations together to form a single large human population of heights, you'd get a bimodal distribution that kind of looks like that. Okay, so now what we can do is we can draw a sample of a particular size. In this case, the size is 5. We can change that if we want, but we'll say 5 from that population distribution. So watch. Okay, so we drew 5 individuals out of this population. They were more likely to be drawn if they had higher probability distributions, less likely if they had lower. You can see most of the heights came out of the sort of near the two modes. And then we calculated a mean, and that was the mean of these 5 sampled observations. And we can repeat that. 4 or 5, there's 5 observations of the mean. We can repeat that again. And we can do it, let's say 5 times. We can do it 5 more times and 5 more times. And let's say we do it 10,000 times. And we can do it 10,000 more times and 10,000 more times. So we've got now 30,000, just over 30,000 repeated samples from this population, and that's the distribution of their means. Now there are a couple of things to notice about this distribution. Firstly, it's not shaped like the parent population. It's not bimodal. It's unimodal. In fact, it's normal. This is a normal distribution. We can guarantee, in fact, that it will be normal. Another thing to notice is, notice that the mean of sample means, the average sample mean, is 14.12. That's the same as the mean of the population, 14.12. That's also not a mistake. The thing about sampling is samples and sample statistics like means have particular properties which we can know and we can use to draw inferences about a population we can't see. So in the real world, we may not get to see the entire distribution of the parent population. And in fact, we won't even get to see a particular distribution of sample means. So if I can clear this, all we get to see, let's say we have a sample of size 20. All we get to see is this. We get to see the people we sampled, and the sample mean, and that's it. And we've got to use these two bits of information to conclude something about this. And that seems like a tall order if we can't actually directly access this, right? We want to learn about the population using just this sample. But there's a couple of key things we know about samples, and if we repeat this again 10,000 times, you'll see we know that the distribution of sample means, we only get to see one of them normally, but we know that the distribution of repeated sample means takes a normal distribution. We know it's centered on the population mean, and we know something about its shape. We know it's normal. And in fact, we also are going to know something about its standard deviation, 1.54 in this case. We can actually, using particular formulas, specify exactly how spread out that distribution is going to be. So even if all we have, if I clear this, even if all we have is this, we're going to be able to conclude something about what the population mean is based on this mean and based on what we know about the distribution of sample means. We know its shape, and we also are going to know something about its variance. So let's go back to the slides in RStudio and figure out how we can use this information about the distribution of sample means to draw inferences from a single sample about a population that we can't see. Okay, so just to review what that simulation showed us, first, the distribution of the means is normal regardless of the distribution of the parent population. That's something called, or it's a consequence of something called the central limit theorem. In this class, we don't prove the central limit theorem. It's rather technical to prove, but we do use it, and we have to know something about it. And what you have to know is that the distribution of sample means from a sample is always distributed normally, and with the distribution centered on the population mean, regardless of the distribution of the parent population. In other words, that's always true, regardless of what the parent population distribution looks like. And that's very important for the inferences we're going to draw starting in a second. Another thing you have to know is that the distribution of sample means is narrower than the population distribution. You notice that from the simulation, it was always sort of more compact. And in fact, there's one more thing we can note, and if we go back to the simulation real quick, if I do 10,000 draws with a sample size of 20, you'll notice that that distribution is narrower than if I have sample sizes of 5. And then if I go up to 25, it gets even narrower still. So if I start at 2, you can see it's really wide and kind of ragged. At 5, it's normal and wide. At 10, it's a little narrower. At 16, it's narrower still. At 25, it's quite narrow. The more sample observations you have in your sample, the narrower the distribution of the means will be. So going back to our slideshow now, those are 3 important facts that you should know, and you can sort of see them demonstrated in the sample or the simulation that we just did. If you want to prove them, you're going to have to take a course that's a little more mathematically sophisticated than this one. You're going to have to learn some tools of proofing. But for the purposes of this class, it suffices just to understand that this theorem implies, the central limit theorem implies these 3 facts about the relationship between sampling distributions and population distributions, right? So sample statistics like means, particularly means, are normally distributed. They're more narrowly distributed than the population distribution, and the average sample mean is at least the average sample mean is identical to the population mean. Okay, so the distribution of sample means is normally distributed. And I hinted earlier that we not only know something about the average sample mean is the same as the population mean, we can also learn something about the distribution of those sample means. And our estimate of the standard deviation of the sampling distribution of the sample mean, our estimate of that is called the standard error. The standard error is called that because it's an estimate of the distribution of the sampling distribution, and it's an estimate of sort of how much error there is, how much difference there is between a sample mean and the actual population mean, right? The average sample mean is the population mean, but we only get to see one sample. That sample could be sort of away from its own mean, the mean of means, so to speak. And so we want to know sort of something about that error, right? What's the difference there? But because of the central limit theorem, we actually do know something. We know a lot, as it turns out. Now, you may remember when we were talking about variance, remember this graph. I believe this graph comes from Wikipedia. When a distribution is normal, we know exactly how often a particular sample mean is going to fall within a certain range beyond the mean of sample means, or the population mean. So here I've designated the population mean as the Greek letter mu. That's the average sample mean. And we know, because the distribution is normal, that there's a 68% chance that a sample mean from a randomly drawn sample will fall within one standard deviation plus or minus of that population mean. We know that there's a 95% chance that it'll fall within 2 standard deviations of the mean, and we know there's a 99% chance that it'll fall within 3 standard deviations of the mean. What this is telling us is, and remember, this only works for normal distributions, but the sampling distribution is normal. We guarantee that with the central limit theorem, right? In fact, the central limit theorem says specifically the sum of a finite, independently, and identically distributed random variable from any distribution will be a normally distributed random variable. So we know it's normal. If we can just learn something about sigma, which is the standard deviation of the sample mean, we can say a lot about what the probable population mean is given an observation of a particular sample. And the central limit theorem actually gives us a way of calculating that. So just to go through this, if n observations of some variable y are drawn independently, meaning they're not linked to each other, it's like you're drawing balls out of an urn or slips of paper out of a hat or something, so they're not connected, and they're from the same distribution, which means the population distribution that we're studying, a single population, all draws come from the same population distribution, has to be the same. Doesn't have to be normal, but it does have to be the same. And y's population distribution has a finite variance and a mean. So there are some technical distributions that have infinite variances. Not really that important for this class. We have to assume that there is a known variance for the population distribution. In those circumstances, then for sufficiently large sample sizes, the sample mean, and you can see I've calculated y bar there. Y bar is just shorthand for what the sample mean is. You add up all the samples, sample draws, and you divide by the sample size. That statistic, the sample mean, is distributed normally with a mean of mu, which is the population mean, and a variance of sigma squared over n. Now, sigma squared is, you can see right here, that's the population distribution variance. N is the sample size. So if we want the standard error, or the standard deviation of the sample mean, we take the square root of sigma squared divided by n, and sigma squared is just our estimate of the variance of the population distribution, and the way we estimate the variance of the population distribution is just to compute the variance of the sample. So if we got a sample of 100 things, we calculate the variance of those 100 things. That's our estimate of the population variance. And then we divide that quantity by n, take the square root, and that gives us the standard error, which is the sampling distribution standard deviation, or at least our estimate of it. One thing that's important to keep in mind here, the standard deviation of the population distribution, right, the variance of the population distribution is not the same as the standard deviation of the sample means, but they are related. In fact, the standard deviation of the sample means is the population distribution, or at least our estimate of the it is the population variance divided by n, and then square root of that is the standard error. So the population distribution variance and the sample mean distribution variance, they are related, but they're not the same. In fact, you saw from the simulation earlier, the standard deviation of the sample means is narrower, and that makes sense because here's the population, or at least here's our estimate of the population distribution variance. You're dividing it by a number. You're dividing it by the sample size. When you divide a number by a number and that divisor is greater than 1, you're going to make that number smaller. So it shrinks the variance of the sample means, right? That intuitively kind of makes sense. So keep that distinction in mind, and keep how they're linked together in mind. A couple of bits of terminology. Anytime we use hats, so this is like sigma hat y bar, sub y bar, that means we're estimating something. A hat means estimate. A Greek letter is a population statistic, and a bar is an average. So sigma here is sigma sub y bar. That's the standard deviation of the sample means. The standard deviation of the sample means, and we're estimating that. That's the hat. We estimate that using our estimate of the variance of y. Notice the difference, that's sigma hat y bar, that's sigma hat y, right? That's the standard deviation of the population distribution of y. This is the standard deviation of the sample means. So we estimate the population distribution variance using just the variance of y. So this becomes this. That's our estimate of sigma squared y. And then our estimate of sigma hat y bar is just that divided by n, and then take the square root. There's a lot of formulas flying around. I swear they will become more familiar as you use them more. And for those students who are taking Pol 280 at Wake, you will have a formula sheet with this formula on it for the exam, so you don't have to worry about necessarily cramming the formula for the exam. But you do need to worry about understanding what's going into this and how it works. And one thing you can try to keep in mind is this population variance. See here, the standard deviation is 6.79. And then this standard deviation of the sample means, this is 1.36. If we were to divide 6.79 by the square root of 25, we should get something close to 1.36. So $1.358, that's pretty close to 1.36, right there. So the variance of this distribution and the variance of this distribution are linked. They're definitely related, but this one, the distribution of the mean, sample means, is smaller than the population variance or standard deviation, and they're linked by dividing this variance by n, and then if you want the standard deviation, you take the square root. Okay, so as I alluded before, the whole point of this exercise is because we want to be able to say things about a population, like American voters or American households, or the population of states in the international system, but we can only see a sample of that. We can only see a particular survey with a limited sample of Americans, or maybe we can only see a certain proportion of the international system that has unfolded over time. We can't see all possible histories. And so we need to know something about what this sample tells us about the population. And so we have to use the sample to infer something about the population. So for example, if we take a sample of American households and find the mean income is $72,886, what can we say about the population mean income? So now let's go back to our studio, look at our sample from the survey, and start thinking about what information we actually have in the sample, and then we'll figure out how to take that information and draw inference about the larger population. All right, so we've got this data from the Consumer Expenditure Survey. Let's look at the probability density of household incomes before taxes in that first survey. The variable is called FINC BTXM. So that's household income before taxes. And I'm going to start off with this command here. And what this is going to do is just show me what the probability distribution is in the sample. Now, that's not exactly the same thing as the probability distribution in the population. We don't have access to the population. But it could give us a sense of what that might look like. It's an estimate of that. And so I've got my data loaded in here. And so all I should need to do is just run that. I guess I don't need, I could just put in the remove na.rm equals true. That won't change anything in this case because it looks like there aren't any NAs to remove, or it's removing them automatically. So we can just leave that out just to make it sort of the command shorter. And what we can see here is just like we saw in the slide earlier, there's a big spike and then a long right-hand tail. And this is 8 times 10 to the 5th, which is $80,000. This is it's outputting this in scientific notation for some reason. I could probably, with a little bit of work, change that to show numbers, although they might not fit on the axis. I might also have to flip the numbers to go vertical to see them well. We could also do the same, present the same information as a histogram. You can see that the density estimate is pretty similar to the histogram, and in fact, if you were really clever, you could plot one on top of the other. But for the time being, you can just sort of flip back between them and see that they have roughly similar shapes. And so this gives us a sense of what the probability distribution of the population might look like, even though this is just a sample. And what it probably looks like is left skewed and unimodal. I'm sorry, right skewed and unimodal. It has a long right-hand tail off to the right, and it's got a single mode. Okay. Are there anybody, I just have it here, is there anyone making 0 income? This is just a variable that's going to be equal to 1 if the income is equal to exactly 0 and 0 otherwise. And it looks like, whoops, there are 4 people in the data set. And I should point out there are 6,301 observations in this data set, n equals 6301. There are 4 people who are apparently making exactly $0 a year. I'm not sure how that's possible, actually, but they're in there. They might be miscodes. I'm not sure. Okay, so we know that or at least we suspect that the population distribution is probably skewed. But that will not matter for the distribution of the sample mean, because this distribution of the sample mean is always normally shaped. So the next thing to do here is going to be to calculate the mean of this distribution and calculate the standard deviation of the sampling distribution of the mean, and then use those 2 bits of information to try to draw some sort of inference about the population mean. So using the sample, we can certainly figure out what the sample mean is, and we can figure out how wide the sampling distribution of the sample mean is. And we already know the shape of the sampling distribution of the mean. It's normal. What we can't figure out is the population mean. That's what we don't know. And so if we go back to RStudio here, I can tell you what the sample mean income in this data set is. $72,886. That's what was on the slide earlier. I could have also gotten that, so that's mean, and then just the variable gives you the mean. I could also have used the summary command, which gives me a little more information, like the median and the first quartile and the third quartile, but the mean's in there too. And I can tell you the standard deviation of the salaries in the sample. The standard deviation is $76,968.25. That's the standard deviation. Now what I need to do is and there's one other thing I can figure out. I can figure out the sampling distribution of the sample means standard deviation. And in order to do that, I need to divide by n. So I need to divide by the square root of n. So this is the standard deviation right here. I need to take that standard deviation and divide by the square root of n. This is the same thing, by the way, as taking the variance divided by n and then taking the square root of the whole thing. Basically, I've already taken the square root of the top, so all I need to do now is take the square root of the bottom. And that standard error of the sampling distribution of the mean is, the SD is, or the standard error is 969 0.63. Okay, well, that's nice. That's all great. What can I do with all that? I need to be able to actually do something with all that. Well, what I can do is I can figure out how likely the current sample mean is under various hypothetical values of the true population mean. So, the way we do this is we convert the information we have into a standardized z-score. And then we use that z-score to tell us, in effect, how likely it is we would see a particular sample mean if the true population mean were equal to some value. And so going back to our simulation here, right here, I'm going to go for n equals 16 just to spread this out a little bit. So let's say I see a particular sample mean, right? Let's say I see a sample mean of like about 20. Looking at this distribution, a sample mean of 20 would be almost impossible to observe. It would be very, very, very unlikely to draw samples of size 16 and get a mean of 20 if the true population mean were 14.12. It would be pretty likely to observe a sample mean of about 14.12. And it would be very unlikely to observe a sample mean of, let's say, 2, right? You can see it very, very rarely, actually really never, occurs in this situation. So what I can do, the logic is sort of slightly turned on its head. What I can do is I can say, if I have a particular sample mean, which population means were sort of most consistent with observing that sample mean? Because there are going to be some population means where I would never or very, very rarely observe a sample mean if the true population mean were some value. And there are some population means where I'd be very likely to observe a sample mean of a certain value if the population mean were truly that. And so what I'm going to do is I'm essentially going to try to draw conclusions about what population means would be likely to produce this particular sample mean. That's how the inference process works. So the first thing I do to do that is I can create a z-score. The z-score is just the average, the sample average, divided by a hypothetical population mean, which I have to specify, and divided by the standard deviation of the sampling distribution of the mean, of the sample mean. And for a z-score, we always set mu of 0, and we set basically the denominator here. I said that wrong. When we subtract the population mean, what we're doing is we're centering the z-score on essentially on 0. So we're subtracting out the population mean so that if that were the true population mean, the z-score would be centered on 0. And it would always have a standard deviation or a variance of 1 because we divided by whatever the standard deviation or in this case the standard deviation of the sample statistic, the sample mean is here. So z always has a normal distribution with mean 0 and standard deviation of 1. The confusing thing here is don't think that we actually put 0 in here. We sometimes do, but we put in basically whatever the population mean is, and when the population mean is equal to that value, z is distributed normally with a mean of 0 and a standard deviation of 1. Whoops. So suppose I get a sample, I get a sample mean of 3 and a standard error of 1.5, and I want to know how likely it is that this particular sample mean came from a population mean with a true population mean of 1. What I would do is I would say the sample mean is 3, the hypothetical population mean is 1, I divide by the standard error of 1.5, and I get a z-score of 1.33. And then what I can do is I can figure out essentially how likely it is I would observe a z-score of 1.33. So going into R here, let me open this up. It might be helpful to see what the normal distribution sort of looks like here. So if I were to, let's say, create a histogram of 50,000 draws from the normal distribution. R norm stands for random numbers drawn from the normal distribution. With the mean of 0 and a standard deviation of 1, which is true for any z-score. This is what I get. I get a histogram centered on 0 and with standard deviation of 1. And our z-score in this example was 1.33, which is about here. And so what this is telling you is, if the true population mean were really 1, we would get a sample mean of 3 in this case relatively often. So going in here, we've got a sample mean of 3, a true population mean of 1, a standard deviation of 1.5. In that circumstance, going back to RStudio here, we would see a mean of 3, the z-score of 1.33, quite a lot. We would see z-scores of like 7 very infrequently, or of like -7 very infrequently. But we'd observe z-scores of 3, often, very frequently. So what we're doing here is we're essentially converting the sample and population information into a standardized score, which we can then check against a standardized distribution, in this case the normal. And R can actually do that in one command. So what we can do here, going back to RStudio, is I can tell it, give me the probability of observing, in this case, a z-score of 1.33. And I believe I have to tell it which tail I want. Actually, let me do this first. Oh yeah, lower tail equals true. What that's telling me is, if I have a z-score of 1.33, that's right here in this distribution, 90.8% of the distribution has a z-score smaller than or equal to that. And so, we see that sort of relatively frequently. You can also do lower tail is false. What that tells you is, and that sort of gives you the area to the right here, what it tells you is that if the true population mean were 1 and the standard deviation were 1.5 of the sample mean, and the true population mean were 1 and the sample mean were 3, we would observe a sample mean of 3 when the population mean was 1. We would observe a sample mean of 3 or larger about 10% of the time. So 1.33 is about here. We would basically, there's like 10% of that distribution is to the right, meaning we would see a sample mean of size 3 or larger. Actually it's about 9%, about 9% of the time. So is that a lot? Well, that depends on what you mean by a lot, but it's certainly not a particularly rare event. If the true population mean were 1, we would see sample means of 3 or larger, given the particular standard deviation of the population. 9% of the time, which it's not particularly rare. So, going back to the original thing here is 90.8% of the time you'd see a y bar of less than 3 if the sample were actually 1, and we would see a sample mean of greater than 3 about 9% of the time. We want the area to the right because what we're trying to assess here is how rarely we would see a sample mean this big, essentially. And in this case, we would see that, a moderate, it's not a rare event, I guess is what I would say. There is some question about what defines rare event. In other words, how infrequently would something have to occur in order to be considered rare? And the answer to that question is there isn't a universally approved frequency for that, but there are conventions. And we'll talk a little bit more about those conventions in a later class. All right, so going back to our problem here, the sample mean of household income is about $76,000. We learned that with the summary command or with the mean command. We learned the standard error with a sampling distribution. I believe that's $969. So we know that as well. What we want to do is construct a z-statistic and then be able to essentially ask ourselves how likely it is we would observe a sample mean of $76,968 if the true population mean were certain values. So we have to construct the z-score. So for example, let's say the true mean were really $76,000. Yep, like that. How likely would it be that we would observe a sample mean of, in this case, let's see, going back to, I think I may have messed something up here. Oh, the mean is $72,000. I was sorry, I was getting that messed up. So the mean is $72,000. If the true mean were $76,000, how likely would it be that we observe a sample mean of $72,000? So we construct the z-score. The sample mean is 72,000, almost 73,000. The hypothetical population mean is 76,000. The standard deviation of the sampling distribution of the mean is 969. We get a z-score from that, and then we find basically how likely would that z-score be to occur. So going back to our studio here, you can see I've already calculated the z-statistic right here, and that z-statistic is equal to negative 3.21. So if I use the pnorm command, so you can see negative 3.21 is like right here. You can see, actually it's closer to like here. You can see that is quite unlikely to occur, right? And in fact, 0.00066, so that would be 0.06% of the time do we observe a sample mean of $72,886 if the true population mean is 76,000 and the standard deviation of the sample mean is 969. What we are inferring from that, actually just to clarify, we would observe a sample mean of that size or smaller if the true population mean were 76,000. So what we are inferring from this is that $76,000 is a sort of very implausible population mean because it's very inconsistent with the evidence. If the true population mean were $76,000, we would very rarely observe this sample mean. And so we're stuck with two possibilities. Either the true population mean is really 76,000 and we just got very, very lucky observing this particular sample mean, or that's not the population mean. Right, those are our two options. And it is possible that $76,000 is the true population mean and we just got very unlucky. But if $76,000 were really the true population mean, we would be very, very unlikely to observe this outcome. And so typically what we would do is we would conclude $76,000 is not a plausible value for the population mean. Now you'll notice I am not saying something that you may want to say. I am not saying, first of all, that $76,000 is not the population mean. Maybe it is and we just got unlucky. I'm also not saying $76,000 is unlikely to be the population mean. I'm not saying that because if we were going to draw that kind of conclusion, we would need to have additional information about essentially what in Bayesian statistics what we would call the prior probability that $76,000 was the population was the true population mean. Without that, we really can't say something like $76,000 is unlikely to be the population mean. All we can say is, if it is the population mean, this evidence is very unlikely to occur. We cannot necessarily jump to that means that $76,000 is unlikely to be the population mean. And the reason we can't do that is because we would need to add our prior beliefs or prior evidence, prior expectations about how likely it would be that $76,000 was the true population mean before we could draw that kind of conclusion. Essentially what we're limiting ourselves to in this case is saying we are going to reject the possibility of population means that are inconsistent with the evidence. That's what we're doing. I also want to note there is a one-step command for doing this. The one-step command is t.test, and you can see what this is telling you here is, you can see this p-value. This is actually giving you a two-tailed p-value. What it's telling you here is that you would be very unlikely to see a sample mean of either $72,886, that's lower than the population mean, or the equivalent on the other side. So the z-score here is negative 3.21. There's also positive 3.21, right? And we can add up the probability of observing a z-score of less than negative 3.21 or also greater than positive 3.21. And that's what it's reporting to you as the so-called p-value. But if you want to do the exact same thing we were doing before, you have to tell it that I want a mean of 76,000, because it's going to assume a mean of 0, which in this case is not a particularly relevant mean to test. We don't have any reason to believe the population mean household income is $0. That doesn't make sense. $76,000 is a more reasonable guess, and so we want to set the mean the hypothetical population mean here to be 76,000. And what this is telling us is, in that case, you can see t is negative 3.21. We would observe if the population mean were really 76,000, we would observe a z-score of less than negative 3.21 or greater than 3.21 about 0.001% of the time. That's what it's telling you. If you want to limit it to the lower tail, you can do that. So going into the help for t.test, you can specify this alternative option. The alternative basically tells it which tail to check. And so if you modify our previous command to sorry. There we go. You can see now we're getting very similar. So we early got 0.00066. We're getting 0.00066 again. There are slightly different numbers past the decimal point, and that's because for this particular case, the t.test uses a very slightly different distribution than the normal. For the test, it uses the t distribution instead of the normal. And for a sample of this size of 6,300, the difference between the t and the normal is essentially non-existent. But for smaller samples, that can be more meaningful. We're going to go into that more in a future lecture. For now, just know that if you use the t.test command as a one-step command, for large samples, it's going to give you pretty much the same answer as pnorm. But for smaller samples, it might give you a slightly different answer. Okay, so the conclusion we would draw here is essentially the true population mean is of $76,000 is very inconsistent with the evidence of the sample mean of $72,886 that we observed. Ergo, it's $76,000 as a population mean income is not a very plausible value. And so we're probably not going to consider that to be sort of a reasonable guess for what the population mean is based on this evidence. You can probably, based on looking at R and looking at the peak here at the z-score of 0, you can guess that the most consistent population mean with a sample mean of $72,886.41 is exactly $72,886.41, right? So if I were to do, for example, the p-norm lower tail with a z-score of 0, which would be if these two numbers here were exactly the same, you get a z-score of 0. you'd see that the p norm for the lower tail is 50%, meaning if the population mean were $72,886, we would see a sample mean of less than $72,886 half the time. And then if you were to do the t-dot test and set this to 72,886.41, and then if, let's say I do the I want alternative equals two-sided, the p-value is 1, which tells me if this population mean were $72,886.41, I would see a sample mean greater than or equal or less than $72,886.41 100% of the time. So essentially that's a very consistent sample mean with a population mean of exactly equal to the sample mean. That does not mean the sample mean is equal to the population mean. What that means is if the population mean were equal to the sample mean, we would be very, very likely to see this evidence. Again, a little bit confusing. The logic is a little bit backward, but that's how this inference process works. All right, so what I'm going to do is we're going to stop here. You can tell from what we've discussed that we have a lot of ground to cover. We've intimated at a few things. We've intimated that there's a t-distribution that's sort of similar to the normal distribution that applies when samples are smaller. We're going to have to talk about that. And we've also left open the question of, we've talked about sort of population means being more or less consistent with the evidence, but we still haven't sort of come to firm conclusions about sort of what set of population means we're going to accept and which ones we're going to reject. And so we have to cover that as well. That gets into hypothesis testing. Both of those topics get into hypothesis testing. And both of those topics are going to be covered as a part of our next set of lectures in our next class. So I hope to see you again then.